Mm. Hi everyone, this is Manohar, and today's topics of discussion are mainly focused on steganography. We will briefly describe and discuss what is steganography and what are the main types of steganography and what are the types that we have implemented, and what are the benefits of one type over the other type, and how we have actually implemented these types of steganography. And we will describe the advantages over the other by walking you through the implementation part and walking you through the outcomes, so that you can directly see what is the advantage of one over the other. Let's discuss firstly what is steganography. Steganography is just hiding a file inside the other file. That means the receiver, until and unless we said the something is hidden in that, the receiver or the viewer can't see any difference between the original file and the sent file. That's the main part of what is steganography. That's it. And let's go through the types of steganography. The types of steganography that we have implemented in this project are just two. Those are least significant bits steganography and Jsteg Steganography. Let's call least significant as LSB steganography. Okay. The main part in LSB steganography is we directly we have a message, let's consider it as a string, and the main here the other part of the file in which we are embedding or encrypting our data into is an image file. Okay. Let's consider we have a text string of the message. Okay, and we have the source file of an image in which we have to embed our message into. And first we have to convert like in this LSB steganography, what we do is nothing but just replace the least significant 2 or 3 bits of the every pixel of the image into our desired message binary streamed binary strings, binary characters. Let's go into how to implement this thing. This is a Visual C++ project which I used because OpenCV library has to be included in this. Okay. Let's go into the driver part. Here it is, least significant bit driver. And firstly we are taking the input of the message text file. You have to create a text file in which you have to add the message of your own. Then we are reading then we are directly converting this message into binary string, vector of bool. That's binary string. Let's go into the implementation of this thing. Convert. Okay. Here we are passing the string itself, and we are returning the result, that is binary string, binary vector. For every string we are converting it into, for every character of the string we are converting it into the binary equivalent of that ASCII equivalent of that character. And then we are pushing back these of course every ASCII character, every ASCII number should lie in 8 bits range, because its range is of course less than 128. So for every character we push back the resultant 8 bits into this result and we return. That's it. nothing fancy here. And then yeah, then we are inputting, we are reading the image of what user want to hide our data in. Yeah, this is just reading the image. And this is the main part, LSB Steganography. Here we are directly converting our image to the desired image. Yeah, let's see how that happens. LSB Steganography. Okay, let's go into it. Okay, here the main part is firstly okay, we have converted this our message into binary vector. That's it. And here our original images. Firstly, we have to calculate if the pixel count in the original image is sufficient enough for our message to be embedded in or not. That is, if our message is too long, so that we keep everything, we keep the last two we replace the last two significant bits of the image of every pixel. Even then, if the image is not sufficient, then we can't do anything, right? That's what I did here. I just prompt the message is too big to store in the image. That's like calculating the total pixel count and if it is sufficient or not. The 16 is in the first 16 bits we are just storing the count of characters in our string, because at the time of decryption we have to know, right, how many characters are stored in the present image, right? Yeah. Next, going to the next part. This whole part is encrypting, embedding the binary information. This whole part is embedding the number of characters into the first 16 bits, like for last two significant bits of first 16 bits, that is 32 bits. Like the normal integer is of 32 bits, right? So we use 16 pixels to store the count of characters. And then the next part comes, here is the actual data, actual message binary string is going into the each pixel of our image. This is pixel count by 3, and this is pixel count by 3 percentage rows, because we don't we should not anyway exceed that limits of like boundaries of our image. This whole thing makes sure that thing, right? Yeah. And here we are considering the color image. Every color image is an RGB image which has each block has three 8-bit integers, like 0 to 255, 0 to 255 and 0 to 255, which each represent RGB components of a pixel. That means we have 3 chances, like 3 into 2, 6 bits. 6 bits of our message stream can be embedded in each pixel, like 3 components of each pixel, right? Because we are embedding only last 2 bits of each pixel count, so that the whole change will be plus or minus 3. That's it. Okay, that's it. Then we are returning the resultant image. Here is the resultant image. This is just to shows the output of the image is not much different than the original image. Okay, that's what steganography is. Then we come to the part of desteganography. That means decrypting our there has to be some decrypting, right? Yeah. That means our decrypting of the image. We have already this resultant image has some binary information which should be which is further decrypted to form original message. We have to this destegno will get the binary string which is embedded in the resultant image. That's it. Let's go to destegno. Okay, this is destegno. We just have the input as an image. This is a very similar kind. The first part will calculate the number of characters that are being that has been embedded in the image, and the next part is directly the extraction of our binary vector from the next from the pixels after 16 pixels, right? Because the first 16 pixels have the count of characters, and we just return this result, which is a binary vector. That's it. Have done LSB Jsteg, and we just left with the extraction of original string from the binary string or binary vector. Like, yeah. This is the bool string conversion. Let's go through this quickly. Where is it? Yeah. Right. Yes. Here there's nothing fancy in this. We just take the blocks of eight binary boolean values at a time, and we convert these 8 into the original integer. What will be the decimal form of that binary string? Then we'll convert this number into the ASCII character. That's it, and we will push back these ASCII character into the string, and we will return that string as a result. That's it. Okay, let's test first. Okay. Okay, I had a test file txt in the same directory, and this is going to take a while to read because it has lots of strings. Okay, yeah, it's done. And doc.jpg. This is the file. This is the image file I want to embed my data into. Yes, done. Yeah, we got 2 images, right? This is the original image, and this is the stego image in which we have embedded our data. Like, you can't see any difference. Almost you can see nothing difference in these images, right? Just you can see that there is a strong highlight of line here, and there's a weak highlight of line here. No one's going to know the fact that there is some data in this, or there is some message in these images. But let's see the only least significant parts, only the least 2 significant bits of both original and stego images, so that let's see what happens. Yeah, this is the only least significant bits of old image. That means the original image. Yeah, and this part here it comes, right? The least significant bits of the encrypted image or a steganographed image. Yeah, we can see a strong highlight of a rectangle portion over here, that which represents directly that there is some manipulation done over the image, right? Even without having an original image, we can clearly say that there is something wrong with this image. If someone is curious enough to extract these two significant bits of the image, then they can easily extract our message, right? Okay, hence it's proved that it is weak enough. It is weak enough algorithm, right? Yeah. So that we have Jsteg Steganography, in which let's close this first. In Jsteg Steganography, we just embed our message into the least significant bits of discrete cosine transform coefficients of each 8 into 8 blocks. Yeah, if it sounds similar to you, it's very similar to the JPEG compression algorithm. Yeah, it's very much similar to JPEG compression. The only difference between JPEG compression and Jsteg Steganography is that's a compression algorithm in which we have to reduce the size of an image. This is a steganographic algorithm in which in the middle part of JPEG compression, we just have to embed our binary string, whatever we converted the text string into binary string into the cosine coefficients of each 8 into 8 block. That's it. Let's go to the implementation part. Okay. We have done this in Python, because the DCT coefficient extraction is far easier. Yeah, where is it? Yeah, here it is. It's going to take a while or a second. Yeah, it is. Okay. Just quickly run this thing. It will be caught. It's done. Okay. Yeah, here these are the import statements. Nothing to worry about these things. Yeah, this is a small functional method, like just to show the image. That's it. And here's the main important part. Like if you know the JPEG compression, then you can easily identify this thing. This is the quality of compression matrices. These are quantization matrices in which we have to multiply these things into our with our DCT coefficients of 8 into 8 blocks. You can see that the shape of this thing is also an 8 into 8. This will give this thing will after on multiplying this will give the components of different 64 64 images of high frequencies and low frequencies. That's it. This 10 means 10% 10% compressed, and 50 is 50% compressed, and 90 to 70% compressed. And if we give nothing, like some other different thing or different percentage as an input to this image, we just return the ones. That means there will be no compression loss. That's what we want here. Yeah. Here just the reading the image. Yeah, reading the image in black and white form. That's what we need here. This is the height and width. That's it. Here comes the important part, the blocks. The main part, the first part of Jsteg compression is dividing the image into 18 to 8 blocks of as many as possible. These 8 blocks will then further be subjected to discrete cosine transform to find the discrete cosine transform coefficients, and then we manipulate those coefficients to add our binary string into the image. First thing, and this is a dividing 18 to 8 blocks. This is a functional code, and the DCT operation should only be done on -28 to -27, like the cosine range is from -1 to 1, right? But the images pixels values will range from 0 to 255. Hence we have subtracted everything with 128, so that it will become -128 to 127. That's it here. Yeah, I have done blocking, and the next part comes here. DCT operation, that means all these things are integers, right? So we want to convert these things into float in order to smoothly get over into the DCT part. Okay, here comes the DCT. It's very simple, as simple as possible, like, right? CVT.dct of every block in FLT blocks. This is float blocks. That's it. We got the DCT, and compression matrix. Here comes the compression matrix, 100%. Why 100%? This is not the compression algorithm, right? We have to just embed our message into the image, so we don't need any compression. We just need 100% accurate the same image, right? So we use 100%, which will, I said that, which will return only once, which have size of 18 to 8, right? Okay. Now for every block in DCT, we do this part, that is we divide the block by compression matrix, the same coordinate, of course. And we trim those to the nearest integer. Yeah, I'm just printing just to see if it has came correct or not, right? That's it. And this part is inverse block. That means of course we have to do inverse cosine transform to get the image back, right? That is the same part. And this part is we are reconstructing the image, with H stack operation and finally V stack operation. Like, we are reconstructing the original image by combining these 18 to 8 blocks again. That's it, and we are printing out the image. Here you can see that I haven't encrypted or embedded a message in the image. This is just JPEG compression. To get an idea, here comes the original message encryption part. This is a functional method. That's it, right? It will take some string and it will return the boolean string. conversion of string to bool. That's it. And this put method is a main important method. This will keep this will embed our boolean string into the DCT blocks. Only if remember one thing, if the DCT quotient is 0 or 1, we are not going to embed any information into that block, which will definitely show a difference in the pixel values, or which will on regressive testing, which will definitely show the visual difference between the original and JSTEC image. Okay, and here the main part is we are going to embed our single bit, not unlike in JSTEC algorithm. In JSTEC algorithm we have done 2 bits encryption to 2 bits replacement, but here we are going to do that just 1 bit replacement only if the quotient of DCT is not equal to 0 or 1. That's it. Here for every block in DCT blocks, we are going into the block sizes, of course 8 into 8. If this pointer will take care of the boolean pointer up to which part is done. That's it. Okay, if this is greater than length of the message, we'll just return DCT blocks, or we'll check if it is not equal to 0 or 1. Okay, if our requirement is 1 and already the least significant bit is 1, we don't have to do anything, right? And if our requirement is 0 and we already have the least significant bit as 0, then we don't have to do anything. And then only if both these things are failed, we have to if the least significant bit is 1, we have to replace it with 0, or if it is 0, we have to replace it with 1. If it is 1, then we just have to subtract 1 from the pixel count. That's it. If it is 0, then we have to add 1 thing, and I'm updating the pointer. The last thing is done, right? That's it. And inverse DCT, this part is the same thing what we have done here. I have just copied and pasted these 2 blocks of code into a single method. That's it. Just to have a functional part, right? Okay, last one bit. This thing will show the difference between the original least significant bits image of the original image and the LSB image of the the steganographed image. We have got steganographed after inverse DCT here. Remember that part. Yeah, that's it. Yes, here the driver thing will happen, like the main function, the file equal to we have read the same text file, and we have kept sorry, good. Binary text, we'll have to do something extra here. Let's go to bin. Bin txt is equal to str to bin of bin txt. I guess let's compile it back. I just forgot before to convert this binary text, the original string into the binary text. That's what I have done here. There's nothing. Okay, then we just call the put function, like it will put our data into that image. Then the final image equal to inverse DCT of the DCT, right? And the last is the final image, least significant bits of the final image, and the first is the image of the least significant bits of the original image, and I'm just plotting those two side by side. That's it. Okay, let's see the difference between least significant bits of the original image and Jsteg Steganographed image. We can almost see nothing. There's nothing different in these two images because we just manipulated or changed the DCT coefficients, not the real pixel count. That's it. The change will be overall the image or overall the block unified or averaged overall the block. So we can't see any difference between the least significant bits images of original and Jsteg. That's it. Thank you.